Hello and welcome to All Space Considered, everybody. My name is Dr. David Reitzel, and with me tonight is Laura Meabron, Ginger Rose Brucker, and Jared Head is our crew. And tonight is Thursday, August 20th, 2026. We do the show live from within the Leonard Nimoy Event Horizon at Griffith Observatory. We also live stream the show, so any of you that are here in the audience, you can watch the next one at home. Any of you at home, come on up and see the program live. There's all sorts of extra stuff you get to experience, as the crowd just saw. We have a terrific show for you tonight. Let's see if I can get our, probably have to turn it, no, it's on. There it goes. So it's the third Thursday of every month we have our show. And tonight we have space news. It's a planet? No, it's a moon. Betelgeuse is not alone. The sun, zoom in, enhance. Zoom in, enhance. We've got the mostest Mars honeycombs. And also we've got a solar eclipse for the ages through the eye of Perishenge and amazing astronomical images, and also out to launch tonight. And then we have a special guest, Imaging Stars with the CHARA Array with Dr. Gail Schaefer from Georgia State University, and she's also the director of the CHARA Array at Mount Wilson Observatory, just up in the mountains right here next to LA. So we're thrilled to have her tonight. This image, that was our background image, is a picture of an eclipse. And as you know, we just had a total solar eclipse. This one was actually from August 21st, 2017, though. And you need to have temperatures of like 3.6 million degrees Fahrenheit, between 2 and about 3.6 million degrees to make this image. Why? Because that's made in iron, glowing iron that's had a bunch of electrons stripped off. So we can actually make measurements of where there are heavy elements glowing like neon glows in a neon sign. So that's the reason this is so colorful and pretty. Well, to start off tonight's space news, let's start with a story about a star that has a brown dwarf orbiting it. This is a brown dwarf. It's an object.
That's no moon.
Uh-oh. That's no moon. This brown dwarf in the foreground has an object orbiting it. And is it a moon? Well, it's the size of a gas giant planet. So what are we going to call it? There's a star with a brown dwarf. A brown dwarf is an object too small to be burning hydrogen like the sun does, but it's too big to be a planet. It glows under its own gravitational collapse and can even burn a little lithium, it turns out. But let's take a look. How was this discovered? Well, it was discovered with a very large telescope down in Chile, and they did it by using spectroscopy. You can measure the spectrum of that brown dwarf, and those absorption lines in the atmosphere wobble back and forth. You can see the dark lines down below going back and forth. Well, depending on how those move, you can measure the mass of the object that's doing the tugging on it. So this is about 73 light years away from Earth, and they had to monitor this to make the measurement. And we're really not sure what to call this thing. Is it a moon? Is it a planet? It's too really big to be a moon. But a planet orbiting a brown dwarf, orbiting a star, this is as close to an exomoon that we've gotten so far. So we're waiting for that really true first exomoon. All right.
Very cool result.
Yeah, very cool result. Our next story is about a famous star in the constellation of Orion. That's Orion that you're looking at there. You can see the belt stars and the sword. Well, up in the top, there's a bright red star. That's the star Betelgeuse. Betelgeuse is 408 to 548 light years from Earth. That actually creates a lot of confusion as to when it's going to die. Depending on how far away it is, changes where it is in its stellar evolution, changes what kind of star it is slightly. If it's further away, well, then it needs to be inherently brighter to look that bright in the sky. If it's closer, well, then the star doesn't have to be quite as bright to look that brightness. So models have some uncertainty to how this star is going to go through the end of its life. And it's close. It's close to the end of its life. In fact, you probably saw stories like this. Is Betelgeuse dying? Is it going to go? What's happening? And the answer is, let's see here. It didn't make it in there. Anyway, anyhow, Betelgeuse did have some dust that was blown off that was making people think it might be dying. So there was a big change in its brightness. Eventually a paper came out and said dust had been thrown off earlier, that its outer atmosphere was puffed off, and then it coalesces into dust grains, dimming the star behind it. Well, this made people wondering, that's a little strange to have dust thrown off so in a big clump, kind of. So folks did some observing of it, and using Europe's Southern Observatory's VLT, they discovered that there is another star orbiting with Betelgeuse. This was thought it might be there for a long time. Well, they used an instrument called SPHERE. SPHERE blocks out the light from Betelgeuse itself, so a little coronagraph, so that bright star is gone that would have been in the middle. And then it also uses some adaptive optics to really sharpen the picture as much as it can. And that little dot with the crosshairs on it, turns out, is another star. And this companion star is about, compared to Betelgeuse, which is huge, it's only about 14 solar masses, so it's still a fairly big star. And its gravity will tug on Betelgeuse, and it will affect the environment around it. And it could cause the atmosphere to clump together and make denser clumps of dust. So the picture of what's happening at Betelgeuse makes a little more sense with this companion star there. By the way, all that mottled stuff you see in the picture that there are not crosshairs on, that's all diffraction. If you take light and you pass it past a sharp edge, you'll get sort of rings on it. And the other optical parts of the camera create sort of those lumps in there. So they're able to tell the difference between things that are part of the camera's optics versus an actual signal they've determined. But that's what those extra dots are in there. So there's the zoomed in picture of it. So pretty cool. Betelgeuse, the bright red star, you now know when you're looking at it, you're actually seeing two stars. Pretty cool.
Pretty amazing stuff. So I think our clickers, there we go. So for anyone here who loves weather, or am I muted? Yes, I am muted. So for anyone here who loves weather or looking at clouds, you might have seen something like this. This is a real picture. These are fluctus clouds. They're also known as Kelvin-Helmholtz clouds. I even heard them called Van Gogh clouds, apparently. And it is formed by what's called a Kelvin-Helmholtz instability, which looks like these crashing waves. And they're fairly short-lived, but they do appear in Los Angeles on occasion. I've seen some over the observatory. So this is a basic physics experiment just showing you how they form. So you really just need two fluids that have different density that are flowing past each other at different speeds, and then you get this interaction that forms these little cresting waves. And that means, because it's pretty basic physics, you can actually find examples of this in many places, not just in our atmosphere. You can see them here in the cloud bands of Jupiter, right above that big red spot, which is a very big storm. And you can even see them here on Saturn in this image from the Cassini probe. And we're seeing this turbulent boundary between two bands that might have these different temperatures that are causing this. Now, one of the most powerful telescopes on Earth has discovered it, or has discovered this instability now in another kind of celestial body. So you might recognize this is the Daniel K. Inouye telescope in Hawaii. And let's have a look at what they actually were able to image. So they just shot the highest resolution image of the sun's surface ever captured. What you're looking at is a really extraordinary image, and they were able to reveal these deformed boundaries of these magnetic elements and these ultra fine scale stripes that are associated with those Kelvin-Helmholtz instabilities we saw earlier. And they're basically like little small whirlpools. Now let's look at the size. This is absolutely incredible. So they've overlaid the Hawaiian Islands on here. This is super, super close-up plasma. That's super hot magnetized gas that makes up the sun. And so they have superimposed the Hawaiian Islands just to show how incredibly zoomed in this is. And let's take a closer look. So they made this extraordinary animation. We're zooming in right now. Those dark areas you see here, those are sunspots or big active region. And this is just to show you how zoomed in this is. Here you're seeing the granulation of the sun's surface. It is convective, kind of like a pot of boiling water. And you're really seeing, they're going to zoom in and show this movement. It is absolutely amazing to get to see this. And this is really important stuff, right? This discovery can help explain how magnetic energy builds up, how it moves around, and eventually that actually fuels solar flares, eruptions, and other phenomena that creates the space weather that influences Earth and our technology. So really, really extraordinary observations. Gosh, it's just It's beautiful, right? It's like a little ocean on the sun that's just very hot. So they just made the cover of Nature with this. If you're unfamiliar, this is one of the most prestigious journals we have in science. So really an amazing discovery, an extraordinary accomplishment for everyone involved.
Yeah, truly remarkable images. Yeah. The sun, 100 times bigger than the Earth, and we're seeing features that are smaller than Hawaii.
Yeah.
It's, yeah.
Mind-boggling.
Mind-boggling.
Yep.
Well, it is time for tonight's Mostest. So, the Mostest, every month we like to bring you a story that once again highlights something biggest, largest, fastest, hottest.
Farthest.
This time I decided to do just the mostest interesting terrain on Mars that I've seen. So it's a stretch, but I wanted to show this. Curiosity, the Curiosity rover, recently climbed up the Martian valley known as Valle Grande and imaged a honeycomb-like structure. This stuff is really pretty weird. It's these polygonal fractures on the valley floor. We've observed patches of polygonal shapes like this before, but nothing quite like this. Here's the region. This is the little valley that it's going up. The 20-foot tall butte that's nearby is known as Miraflores, topped by a thick coat of sand actually on the top, so a beautiful landscape there. But you notice right below the rover there, it looks a little strange. The pattern on the ground is a little odd. And when we zoom in on it, maybe I should use yours.
Clicker, let's see. Clicker's having
There we go, the clickers were having issues. When we zoom in on it, this is that. Look at these strange polygonal features. What the heck is going on? I thought it looked like a little one of those wafer cookies, the crunchy ones that have the icing in the middle.
Mars.
Yeah, I could go for a strawberry one.
Does this have a creamy nougat center as well?
Creamy nougat center in the center. But what I think is striking about this is that it's layered. I could understand having sort of a cracked surface of like a dry lake bed or something like that. But this almost looks like it happened over many millennia. You had a lake bed laid down, cracks formed, lake bed, more cracks. But I'm not sure. I'm not a geologist necessarily. I read about it, and it does seem like water and sediment was involved in this, and the sediment that filled these cracks was harder than the other materials, so the materials are eroding away. But we can...
That's so interesting.
This is some of the weirdest terrain I've seen on Mars. Now, this is the time of year. Normally, I'm off out here. I'm not there this year. This is the dry lake bed out where Burning Man happens.
Basically Mars.
Basically Mars, it kind of is. But these cracks form after a rainstorm, and it dries out, and the cracks will happen there. So that's where my brain went, if it's a similar sort of process happening.
Yeah.
And anyway, I kind of miss being out there, but I actually help a crew drag telescopes out to that event every year. So totally interesting. But this year, we're here talking about Mars and the cracks on the Martian surface. Maybe one day they'll have a festival there. Now, there is a weirder rock on Mars that's been found. And Perseverance found this rock, and a lot of people don't seem aware of it, yet I find it stunning. These little tiny features in there are called leopard spots. And this was found at Shayava Falls in Mars, Jezero Crater in July 2024. Scientists still, after all this time, the best explanation for those sorts of features could be life. They don't know another way to make these features. Maybe high temperature, a high temperature environment you could make them, but there's no other signatures of this rock having been at that temperature. You'd expect to see other things indicating this rock was hot, like in a hot spring. Those aren't there. So, if you want to know, do we have any evidence that Mars had life on it, this is it.
Yeah.
It's not good evidence yet. It's not 100%. It isn't a slam dunk like you'd say. But, boy, it's strong. And they took samples of this. Those samples are laying on the surface of Mars, or they will be if they haven't been dropped yet. We had a mission plan to go pick up those samples, bring them back to Earth, study them with labs that would be able to say, yes, that was life, or no, it wasn't. You need too big of a lab. You need to send a huge lab there. So that's not planned right now, but maybe one day. What do you think? Yeah, that's what I think too. Perseverance is looking like you're going to come get it? You're going to come pick it up? What do you think, Earthlings? So I'd love to have that happen someday. I want to know, was Mars alive? It's a question we have the capability to answer, and we should.
Yep.
Yeah. Well, Jared, I think it's time to take a look at some rockets.
Yeah, I think we should. Let's go ahead and get this. Let's get this party started as soon as it lets me go. All right, we ready to lift off, everybody?
Let's do it.
Clicker is a little slow.
Yeah, I was going to
today.
say we're getting it today. Thank you so much. 4, 3, 2, 1.
Boom.
Boom! Out to launch. Well, maybe not boom. Maybe not
Maybe
boom.
not boom.
That's a bad thing. I remember I took my dad to his first ever rocket launch, and he was like, "Bada boom," and I was like, "No. Like, we don't want that to. I'll actually steal your clicker.
I think it's where you're pointing at.
Okay,
That actually,
so I'm going to get up forward here a little bit. Well, our first one that we want to talk about for this edition of Out to Launch is lucky number flight 13 for SpaceX's Starship vehicle. And it looks like they finally had a flight of Starship, specifically version 3 here, that sort of did what they actually needed it to do for the most part. Not 100% successful because there were many goals, or there was one very specifically big goal that was not accomplished, which was landing the booster. Because once again, they lost engines on entry with it, and it was aimed for the Gulf of Mexico, so it's fine. Here's the stage separation. I love seeing those little Raptor sea level engines swivel back in after they've swiveled out. Here's the view from the boosters that's going into the Gulf of Mexico. And it's not, you can tell it's not slowing down enough. So, and then, I lost it. So, so that was a little tough. But they got it to its suborbital trajectory there with main engine cutoff on the Starship upper stage vehicle there. And then they actually deployed some real Starlink satellites this time. These are their bigger versions of Starlinks, and several of them had cameras on board. This is one of them that had 4 cameras to make a composite. And the Starlinks were sending this image down to SpaceX Mission Control in real time as they were inspecting the heat shield, which you can see in this area right here, those tiles. They wanted to see how does the heat shield fare before re-entry, and it looks like it did a pretty good job of all those tiles staying in place for the most part, which is good. That's what you want. Then they go through atmospheric entry and landing in the Indian Ocean. So here's what that looks like, starting up 3 engines, kind of going from the belly flop to pitching upwards to vertical, from down to 2 engines and then down to 1 engine just above. And there we go, in the ocean. Now last time it exploded, but this time it just kind of fell in the ocean. It was hanging out, everything was nice and fun. Not on a platform, so these are not expected to actually survive landing in the ocean. But this one did, and it did, and SpaceX was actually able to get some of their ships out to it, and they have dragged it back to the Christmas Island near Australia, and now they're going to basically bring that to the shore and tear it down and look at it with their engineer group. So, which is going to be hugely advantageous for them. So I feel like a lot of the issues that they've been having so far in the Starship program should hopefully be mitigated by the work that they're doing with this in Christmas Island right now. And very interestingly, this is the largest human-made object that has gone to space and returned intact. So I didn't realize that.
This is larger than the space shuttle?
It is larger than the space shuttle. The space shuttle is 122 feet long. This is about 180 feet long. Oh, wow. So this is a big one. Wow. And that's not our only SpaceX story this month. We also had this, which may seem rather inconsequential. This is a Falcon 9, a 2-stage rocket that SpaceX uses. And this was a very specific one because this launched the Hakuto R, the second Hakuto R mission for Japan to land on the moon, and also Firefly Alpha's Blue Ghost mission, which ended up being the first commercial lander to successfully land on the surface of the moon. But what we want to talk about is specifically this part of the rocket right here, the cleaner upper stage right there, the non-soot covered upper stage, because after it delivered the Hakuto R number 2 and Blue Ghost landers on their trajectories they needed to go on, it was heading out. And it just kind of hung around Earth, Moon, space. And then just by way of gravitational interaction, it eventually was put on a trajectory to slam into the moon. And it did so on August 5th. And we actually have an image of the crater that it made coming in, and it was a good, substantially sized crater. So we're going to probably need one more here to get the animation started to see it, and there it is.
Wow.
A new crater on the moon, courtesy of SpaceX. So there you go. Now this, there was a very big amount of sensationalism over this story, but it does bring up some things, like if we're going to have a permanent human presence on the moon, we do need to think about not slamming objects into the moon, right? Like if you have a moon base, you tend to not want ejecta from an impact to get close to it. But just for a little bit of perspective, this kind of an event happens about every 6 days on the moon. So something of this order, or this amount of energetic release.
But not something human-made, right?
But not human-made. This is looking it up. So this isn't the first time we've actually smacked stages into the moon before. During the Apollo program, after Apollo 12 had dropped off a seismograph, Apollo 13, they actually used the upper stage of that Saturn V to smack into the moon and then read the seismic waves coming from it and determine the moon's interior. Right. And they did that up until Apollo 17. The first time that we unintentionally dropped a stage on the moon was actually China's Chang'e 5 mission, which was a lunar sample return from the far side of the moon back in 2022. And if anybody's keeping score, this was actually the 104th human object that's accidentally smacked into the moon or been left on the surface of the moon. So again, not unprecedented, but also something that we should definitely start thinking about if we're going to send people to live on the moon.
And a lot of people were trying to image the plume as well.
Yes.
It was kind of a mad dash.
Yeah, I saw the imagery from the European Southern Observatory's very large telescope, which is one of the biggest telescopes in the world, and it's like a little whisper coming off the surface of the moon.
Some folks did get, I think, some spectroscopy of it.
They did, yeah. They detected sodium, which is in lunar regolith, and they also detected lithium, which is what rocket stages are made out of, usually aluminum lithium alloy. So they were able to detect the lithium from that. So very cool. They were able to do that, and I think you're just going to have to move for me there today, because this next one is
we're all
trying.
So maybe I'll do it. All right, this next story also we're going to start our second story in China as well. So this is one of their Long March rockets, and pay attention to what it does. Oopsie.
Oh, that's not
That's no bueno. So it looks like they're joining a couple American companies and others in hot rocket summer, as it's been, since we've been blowing up a lot of rockets here in the United States lately. And now China's getting in on it. This was a communication satellite, so no people on board. But look at what the rocket does up at top.
Oh,
it literally folds at about 2/3 of the way up. So that's the third stage of the rocket, coming undone during a period where the air pressure as it's traveling through actually is at its highest, what we call max Q. So don't know what happened. Don't know if we'll ever know what caused this. But there's some ideas that it was structurally related, because you can actually see coming out of the fireball here is the first stage of this rocket, and it's still going. So that tells us that this was not an issue with the first stage, that it was something further up the rocket as well.
The first stage had plans.
Yes, it did. And the third stage just ruined it for everybody, as it just so happens. All right, this next one is China continuing their rocket work as well. It's like, who's going to get it? So this is from Land Space, the GQ3 rocket. Boy, they love their drone shots, let me tell you. Those were the least dizzying drone shots in this in this video. But this is a very interesting rocket. This is a medium orbital class rocket. So this is going to compete with things like Falcon 9 and Vulcan here in the United States. And you notice that it's got something at the bottom, which is going to come in handy a little bit here. Again, drone shots that are just fantastic here. That's great. As an engineer, I want that. But take a look at what the first stage does here. Not in real time, but this is what it's going to do. It's aiming back down at the ground. Now, why is it doing that? Because it's going to come back and land. And if that looks familiar to you, it's because that design looks very similar to how the first stage of a Falcon 9 lands. And in fact, here it comes down to a landing pad out in the desert in China. And let's see how it does as it is on approach, kicking.
These are real images.
These are real video from that flight. And there you go, landed. Wow. So welcome to the show, Land Space. So just in the past 10 months, we've had 3 companies and groups join SpaceX in landing a rocket, an orbital class rocket. So
incredible.
Yeah, so reusability, which 10 years ago we said was the future, is turning out to be the future. In addition, also want to celebrate this as well. Get your flags out, Laura May. It's Sophie, I don't know, who is an astronaut on the International Space Station right now. She became the first French woman to perform a spacewalk just a few days ago. So congratulations, France, and also parts of Europe as well. So good job. Yep, good job, everybody. Proud of you.
She had some great comments about it, about saying how, when you're outside, and even though they train in pools, but you really can't tell what's up or down or where anything is. And I thought it was nice for an astronaut who are, they're so well trained to say, oh, this was hard.
Yeah, not as easy as it looks.
Yeah.
So very, very proud of her, and what a great accomplishment. And then also going to Europe as well. I don't know if anyone here is a big skateboarding fan. I'm a very big skateboarding fan, both the sport and the culture. This is Danny Leon, who's a Spanish skater, and he was out to do something that nobody's ever done before in what he called the shot of a lifetime. So if we take a look, this is him doing some of the prep work with his skateboard, and they've got a quarter pipe out there where he's actually going to be doing some tricks. Now, why would he be out in the middle of nowhere doing some tricks with a camera that was literally placed a half a kilometer away from this quarter pipe? Why would he be doing that? Well, it was to get some really cool videos and photos of him silhouetting the sun. Now take a look at some of these images that we got right there. Now, something was happening with the sun in Europe.
What was happening?
Just recently, right?
Just a week ago.
So he's practicing here because they're trying to get him to go to the quarter pipe as fast as possible. Now, why is he doing it in the dark? Oh, wait a second. He's taking the photos in front of the eclipse. He's also taking the videos in front of the eclipse. So we figured does this count as a launch? I'm just going to say it counts as a launch. It's really cool. And this will lead us into talking about that. Look at this.
Yeah.
Incredible, right?
So the shot of a lifetime, and then the photo that comes out of this too.
And I mean, people spend years planning some of these shots before an eclipse and lining things up and practicing.
And it's so really amazing that they got this shot perfectly at the beginning of the exit diamond ring from it.
And it was we'll talk about it more, but it was a very, very short totality.
Yeah.
So getting a shot like this, really the timing, oof.
Yeah, Danny said that it was about 40 seconds to get it right.
Yep.
Yeah.
So,
or
crazy.
you miss it completely. So and that's our out to launch.
Well, we have a launch coming up.
Yes.
On Sunday, August 30th, the Nancy Grace Roman Telescope is expected to launch. We're very excited about that.
really exciting.
Yeah.
This is a Hubble-class space telescope, so the mirror is basically the same size, but its field of view is enormous. It's going to open up a whole new window in space observatory.
Yeah.
So very exciting.
Lots of exoplanet discoveries.
My favorite
hopefully.
story about this is that in 2012 the National Reconnaissance Office, which is who builds and operates the spy satellites for the United States military, contacted NASA and said, "Hey, we have some hardware from the 1980s. Do you want it?"
Yeah,
and NASA was like, "Yeah."
No, that's not what NASA said.
So,
No, that's not what most of the astronomers said. Most of us said,
"Oh yeah,
no,
you guys didn't because it would be more
we don't
expensive."
want these. It actually was more expensive to
Yes,
retrofit
I'm
or
sorry
whatever,
about
but it took many panels and many groups and many whatever. And they came up with a plan and a set of instruments on it that made it worthwhile. So it is revolutionary, but how they initially proposed it, we could just build another Hubble cheaper than retrofitting this thing. Yeah. But somebody came along and said, no, the design is good. You just need to open your eyes and look at a little different direction.
Yeah.
So we
cool.
were wrong. Astronomers were wrong off the bat because now we're very excited to have it. So it's good.
Still
but now NASA was excited. It was the astronomers that were like, huh?
No plans for the second one. But the stipulation is you can't point it at the Earth. So, so
not allowed.
All right, so now before we go back to the eclipse, we're going to bring you another kind of beautiful celestial alignment. And this one was between our star and a human-made structure. So maybe you visited us during an equinox or solstice. Maybe you've seen such an alignment on our West Sunset Terrace. Take a look if you're here on the way out. Or maybe you visited Stonehenge in the United Kingdom. It's a very, very famous structure.
That's not Stonehenge.
That's not Stonehenge. Thank you for acknowledging this.
I don't even think that's in England.
Back in our January episode, we spoke about one alignment that takes place in Paris, in France, not California, on the Champs-Élysées, which truly gets to earn its title of most beautiful avenue in the world during what is now known as Paris-henge. So let me see. Now I'm the one struggling with the remote. We're like people with remote controls. We've been abandoned. There we go. So twice a year in May and August, for a couple of days, the sun aligns perfectly with different parts of the avenue, and it sets right beneath this beautiful, majestic Arc de Triomphe that was commissioned originally by Napoleon. Now, the event is attended by hundreds of people who do camp out for hours in between cars and buses to capture this perfect alignment. I shot this on the first night. I showed up, I think, around 6:30 p.m. And keep in mind, the sun wasn't setting until about 9:15 p.m. So people were out there for quite some time. And here's the crowd at the, let's see if this plays. Maybe not. There we go. So here's the crowd at Place de la Concorde. So all the way at the bottom of the Champs-Élysées on one of those evenings. This was during a heat wave, by the way. So everyone there is braving the heat wave. This is about a half hour before the alignment actually happens. You can see it. Everyone's looking in that direction, worried about a bus or something stopping right beforehand. And you can see where the sun is in comparison to that arc.
So all those people came just for that?
Yep, all those people came just for that. It is in the news quite a lot now. And here's a little time lapse of it happening. So you can see the sun is aligned. It actually follows those trees. And so for a couple of days, you're going to get to see this. Keep in mind, the sun will move by about half a degree on the horizon. So every single day, you get to see it ever so slightly differently. And then boom, right dead into the center, and it is extraordinary. It is like a tunnel of light. So I was able to be there. We had also a little bit of cloud on one day, which actually created these amazing crepuscular rays. You can see this crowd right in front of me that was observing this. This was shot from the middle of the Champs-Élysées. And that was when, again, we had right when it was in the middle, one of the nights, we had a cloud. That's how it happens. We also had a bus that stopped right in front on the same night. But, so this was one of these pictures that I shot of it just being perfectly aligned, dead center. It's also very quick. So same as the eclipse, this kind of, the sun, we are moving very quickly. And so you really have to be very fast at shooting these. And I was trying to reproduce this image, which my father actually shot 30 years ago. And I realized that this image cannot be shot again. Obviously, if any image you're trying to reproduce, it's very hard. The light might be different. But the reason that this is a very difficult image to reproduce is because pollution in Paris has actually halved in the past 30 years. And that was creating some of that beautiful filtering. On some of these images, you were able to see sunspots. No more. The air is cleaner. But the sun looks a little brighter, so there you go. So you can show up twice a year and actually get to see this alignment.
Was this intentional or a happy accident?
The
fact that it lines up with the sun.
No, I'm pretty sure Napoleon. I don't think Napoleon was into astronomy.
Okay, so it's just completely accidental.
It's just accidental. I mean, the movement
awesome.
of the sun is quite wide, obviously, over that stretch of time, and so you do get to see it twice a year. But yeah, happy accident. And Paris is not perfectly aligned, having these kind of east-west, north-south, and so, it's just a happy accident that it happens. Now, staying in Paris, here's another Parisian monument you may recognize. Anyone know what this is? Eiffel Tower, right? So, Wednesday last week, just a week ago, millions of people on Earth were able to witness another incredible solar eclipse. Here it is in its partial phased, visible right behind the Eiffel Tower. So here's a map of the visibility. That dashed line is where you can actually see the phase of totality. So you can see it went through Greenland, Iceland, and Spain just for that total section. And the other bands, that's where the eclipse was partial, right? So many of you asked, actually, the observatory, you came up here, you called us to know if it was visible in Los Angeles, apparently. Unfortunately not. But the partial phase was visible from Alaska, parts of the Northeast that you can kind of see here shaded in yellow. And this was the first total eclipse visible from Spain in over 100 years. Wow. So the last one occurred on April 17th, 1912. You're seeing a very old report on it, people observing it 100 years ago. And there's a really interesting connection to a historical event because this eclipse in 1912 was 3 days after the sinking of the Titanic, which was partly caused by the kind of moonless night that will precede an eclipse, right? You need a new moon in order to have a total solar eclipse. And in this case, that moonless night prevented them from seeing that fatal iceberg. So eclipses cause ships to sink? No.
Yeah.
That's a weird correlation. But eclipse mania is not a new thing, right? So here's a cover of a French newspaper because a phase of this hybrid eclipse from 1912 also went through France, and so it was watched by about 2 million Parisian people. Keep in mind, this is 1912. That's 2 million people who are doing astronomy 100 years ago out in the streets. And the famous term of the diamond ring effect that happens right before totality when you get to see just that little bit of light filtering through the mountains of the moon. It was actually coined by an article from the French newspaper Le Figaro talking about this very eclipse. He overheard a woman say that it looked like a little diamond ring. Now back to present day, we don't just have one eclipse, but what Spain is actually calling a trio of eclipses going through the country in 3 consecutive years. Now this is an extremely rare astronomical coincidence. Statistically, this would occur about at the same location or having 3 like this roughly once every few centuries or once per millennium, and it means a lot of tourism. Spain had an extra, they were estimating right now about 400,000 to 500,000 extra people, including Ginger and myself. We showed up there. So this is a real sign on the highway. For any of you who can't read Spanish, it says, please don't drive with eclipse glasses on. If you've ever tried eclipse glasses, that would be definitely a dangerous thing to do.
Yeah.
Now the Spanish government is actually putting a lot of work into making these eclipses safe for everyone. There we go. So there were also many driving restrictions. We were warned on the day about potential very heavy fines if we stopped on dirt roads. There were fines for photographing the eclipse while driving. Obviously, we don't want to do that. And much of this was also to prevent more of the fires that have devastated many parts of Europe this summer. And even though there was no totality in France, eclipse mania was also very present. Pharmacies over there, they are distributing free eclipse glasses. And this was a park in Paris just during the eclipse, again, just to observe the partial eclipse. Pretty extraordinary. This is people in the Pont Neuf who are observing that partial eclipse. You can already see that light is a little bit dimmer. It was about 90%, I think, in Paris. And I'm going to give you guys a little reminder for anyone watching. We should always talk about this with every eclipse. You should always observe an astronomical phenomena like a partial eclipse, but we do have to repeat that totality, it is a completely different, transformative experience. Yeah. We even say it is basically like night and day, literally. Yeah. And I'm going to echo the tagline of this XKCD comic strip that shows the difference. A partial eclipse is like a cool sunset. A total eclipse is like someone broke the sky.
Yeah.
Yeah.
So,
I often like to say it's like being told what it's like to have chocolate cake versus having some chocolate cake. Yeah,
you know,
it's that different. It's a completely different experience.
It really is. So if you ever get a chance to, there are people, you know, who live next to Total. I met lots of people in Madrid who were like, oh, yeah, it was, you know, just a kilometer away, and they didn't go. And so, you know, we encourage everyone to do that. But a major reason why you want to observe totality, it's also because it's the only opportunity to observe the solar corona. So this outermost part of the sun's atmosphere, which stretches out for millions of kilometers, it looks different for every single eclipse. Now what you're seeing here is the prediction that's created before every eclipse by the California-based company Predictive Science, along with the Astrophysics Institute of the Canaries. Now they use the measurements of the sun's magnetic field to construct this 3D model of the solar atmosphere, and then they just calculate the angle at which we will see it from Earth. So this was their prediction. It came out a couple days before the eclipse, and they refine it. And here it is compared to an actual image they shot of the eclipse. So you can see pretty remarkable how well it lines up. Pretty amazing work. And by the way, again, a little bit like that discovery we spoke of earlier, this helps us understand the solar wind, how it affects us, how it affects our technology. Now, totality is also your only chance to see prominences with the naked eye. Those are these big plumes of plasma, which they glow in this pinkish red light. You can actually observe them in our solar telescope. And this is what the sun looked like a few hours before totality. So that little bit you're seeing, it almost looks like a little piece of broccoli that's sticking out there. That is a couple times the size of the Earth, and that is what we got to see with the naked eye during the eclipse. And here it is also from a satellite. So you can see that little reddish shadow that comes in. That is the moon's shadow as it races eastwards, and eventually it crosses that day-night boundary. So it's a very cool thing. You get to see it on the satellites as well. And you get to see, let me play this. Let's see if it's going to actually play. I might need to give it a little extra click. We're all struggling here. There we go.
One of us.
So you get to see, here's a time lapse I took of the actual eclipse. You actually get to see what phase we're in from that little reflected crescent. Oh, eclipse of Laura May. But here you go. You got to see that shadow. You get to see kind of the full shadow on the sky. And that wasn't the end of it, because this eclipse was actually occurring very late in the day. The ones that happened in the United States in 2017 and 2024, they were very high up in the sky. And so you actually got to see the partial phase somewhat with the naked eye. We don't want to tell people that that's safe to observe, but that's basically like observing the sunset. So here's an image I got of it as it was setting. So this really weird sunset that we got to see of this half-eaten little sun. Here is a very cool image that I found online. This was someone who was shooting a little movie of the eclipse. And you'll notice there's a little 3 at the bottom.
Yeah.
That is a balloon that just randomly, a child's birthday party, evidently, got caught just in this person's shot. Raised a lot of questions.
Aliens.
The sun got tattooed.
The numbers are out there.
And of course, we get lots of images from the partial. So this is an image I shot with a Veonis Vespera of just these beautiful little sunspots, and just at the very start of the eclipse. But Ginger, you have more images for us.
Yes, that's right. Okay, let's see if this works.
Let's see if you're
That's right.
Amazing astronomical
clickers work.
images, I know. You might have to do it for me.
Let's see. We're just all wildly clicking here.
We are.
This has never happened before. They're on strike.
They are on strike.
Okay.
There we go.
There we go. So this first picture, even if you weren't in the path of totality, you could still experience the eclipse. I saw this picture, and they had this on the screen at a Red Bull arena in Austria before a soccer match. So pretty cool that they had this during the game.
Nice.
So
It's round. It fits.
exactly,
It's just like a football.
right? I would be distracted though.
Yeah, right.
Yeah.
And then some other pictures that we have.
Let's see. There.
So I love this one with the foreground and the people just experiencing the eclipse. This was in Salinas, Spain. So pretty cool. The moon is actually covering completely. This is during totality. Pretty amazing shot. You might have to do it. It's really struggling.
Absurd.
This one was super cool. You can actually see this was in Burgos. So where we were originally thinking
So
of
really
going.
right in the center of the path of totality. They had the longest possible totality there. About a minute and a half, a little longer.
Yeah.
we
And this
go.
one was cute. I had
that
to. So
is
it's just
so
a
nice.
composite of the entire. You can actually see each little phase of it, and then totality there in the
Sunflowers.
middle, and the sunflowers.
That's from
are super pretty.
That's from Bill Ingalls, who's like NASA's top photographer.
Oh, cool.
So
Oh, okay. Yeah, that
he
was
does
on
great work.
the NASA site. And then this next one was just so cool. This is part of what the diamond ring that you mentioned earlier.
Yeah.
So diamond ring part is really fun to see as well.
And that little prominence that we showed you earlier, so that is more of its color that you can see here. It's kind of hydrogen alpha light there that's pinkish.
Yeah. And this next one was really cute, an eclipse of the heart. Everyone know that song?
Bonnie Tyler,
yeah.
Eclipse.
Bonnie Tyler passed away
That's
about
right.
a couple months ago, and so
Yeah.
a nice tribute.
I know. And then, this one was also really pretty. I think this was just a little bit after, so you see it peeking out again, kind of going into that diamond ring. And then This was where we were.
Yep.
This was our setup. I had my camera there, so this was during totality. I snuck back and took a picture with my iPhone. And then here's a diamond ring that I got. It was really pretty.
It's very nice.
So awesome. And another one. This is after the eclipse. During
the partial
totality.
phase. Yep.
This was the partial phase after during sunset, and then here's a little video during totality.
Nice. And there was, in fact, we were talking about it earlier, this kind of orangish glow because it was very low on the horizon.
Yeah.
And so that was what was exciting about this eclipse, is that you get to have this, they're always different, but especially for one that's low on the horizon, you can have different effects.
Well, it was a lot larger too.
Yeah, and
so
it
you
looked
could
a lot
actually
larger.
see it.
Yep,
I mean,
that
usually,
moon illusion.
Yeah. And then speaking of eclipse, this is a bonus eclipse. This was actually released yesterday, so August 19th. This is the Perseverance rover actually saw a solar eclipse on Mars. So I thought that was really cute. I had to throw it in as part of our eclipse section.
One of the two moons, right?
This is Phobos.
Phobos.
Yes, Phobos.
Yeah.
So really
Very cool.
Yeah.
Well, send us your astro photos, and maybe you'll include them, Ginger.
Yes, definitely. If you did get pictures of the eclipse anywhere you were, even if it's in the partial, feel free to send them to us.
Yeah, it'd be
we'll feature
fantastic.
it.
And eclipses do come in pairs. We mentioned it to some of you earlier. So let's see if we can get this up.
Here it comes.
So in just a week, we will have exactly a week's time the partial, practically total lunar eclipse. It will be visible from the observatory. You don't need telescopes to look at it. You can just see it with the naked eye.
Yeah.
But you're welcome to come here. We will actually be open.
Yep, the observatory will be open, but if you want to come early,
Yeah,
the crowds
it will
can be immense,
it will be
and
crowded.
they'll shut down your access to come in if it gets too full.
Yep.
So we don't want you traveling from a large distance thinking you could roll up 5 minutes before the eclipse starts. That won't work.
And we will
So-
be streaming it as well.
Yeah, we will.
So you can
Yeah.
watch it online as well, and this is where it will be visible. So if you're watching us from another country, know that a big portion of the world will get to see this. Most of the Americas, a little bit of Europe and Africa. So hopefully you get to enjoy this lunar eclipse.
And it's just partial here, 96%, so
Yeah.
you won't get the 100%, but so close. It's practically total.
Practically total.
Practically
Yeah.
total. Well, thank you so much, everybody. And now it is time to invite our guest up. So, everybody, we have Dr. Gail Schaefer, Director of the CHARA Array up at Mount Wilson, talking about imaging stars with the CHARA Array. That's right. Our own sun is not the only star that we have images of the surface of. And come on now, Dr. Schaefer, everybody, let's welcome Gail. Thank you so much. And welcome to All Space Considered.
Hopefully you fare better with the clicker than we did.
No, you're fine.
All right, can you hear me? Yes. All right, and I think I just have to change that. Okay, hi, thanks. It's great to be here at Griffith Observatory. So I'm just coming from over at Mount Wilson Observatory. And tonight I'm going to be talking about the CHARA Array. So this is an array of 6 telescopes up at Mount Wilson, and we combine the light from the telescopes together to produce the resolution of a telescope that's 300 meters across. So extremely high resolution. As you heard before, we actually have the resolution that's large enough to image the surfaces of the stars other than the sun. So during the talk, I'll give you an overview of the array and talk about some of the recent science highlights that come out of the CHARA Array. Okay, so this is just to put this all in context. So here we are down at Griffith Observatory, and Mount Wilson is just up in the San Gabriel Mountains, just basically north of Pasadena. So we're just up over there. And so astronomers often want to build bigger and bigger telescopes. And there's 2 main reasons why you might want to build a bigger telescope. One is that the bigger your mirror is, the more light collecting power you have of the telescope. So that lets you see fainter and fainter objects. And there's a second reason why you might want to build bigger and bigger telescopes, and this is that as you build a bigger telescope, you can get better resolution and see finer details on the objects that you're looking at. So this is just basically a tour of different telescope sizes through the ages. And since I'm coming down from Mount Wilson Observatory, I start with the 100-inch telescope that's up at Mount Wilson that was built by George Ellery Hale, and it was completed in 1917. So the 100 inches corresponds to the size of the primary mirror, and at the time that the 100-inch telescope was built, it was the largest telescope in the world. And it remained the largest telescope in the world for 30 years until Hale built the 200-inch telescope at Palomar Observatory, also in California. So until that was, again, 1948-49, that Palomar Observatory was built. And then in the 1990s and early 2000s, there was a bunch of 8 to 10 meter class telescopes that were built. So this is basically gives you 4 times the resolution of this 100-inch telescope. And currently, there are several 30 to 40 meter class telescopes, these extremely large telescopes. And that will basically triple your resolution of these 10 meter class telescopes. And likely, these 30 to 40 meter extremely large telescopes are going to remain the largest telescopes for a while, just because it becomes cost prohibitive to build telescopes even larger and technically challenging to make them stable enough. But there's a way you can get better resolution by using smaller telescopes. And so one way you can get better resolution is to build a bigger mirror. And the other way is you use smaller telescopes and separate them by a distance, but combine the light together. And this is an array of telescopes that work together to kind of simulate a large telescope. So this image here is of Mount Wilson Observatory in the big white dome in the center. Let me just bring up a pointer. Yeah, the big dome in the white dome in the center is that 100-inch telescope that was built in 1917. You see some solar telescopes out in the distance, and the CHARA Array telescopes are much smaller. So there's 6 of them, and I've highlighted them with these yellow circles. So there's 6 of them, and they're built in a Y configuration with 2 telescopes in the south, 2 in the east, and 2 in the west. And these telescopes act together like a big, enormous telescope. And so the separations between the telescopes, the closest pair is 34 meters, and the longest pair is 330 meters. And so basically, if you take one of these 30-meter telescopes that they're currently developing and building, that 30-meter telescope is going to fit between our closest pair of telescopes. So our resolution on this longest baseline is about 10 times better than the planned single telescopes. And so what we basically simulate is a telescope that is 330 meters in size. And so we get the resolution of that telescope, but not the light collecting area. So we're limited to very bright stars, but we get to look at these stars in very high resolution. And so essentially, if you think of a metric to what our angular resolution is, if you take a nickel coin, you can basically resolve the size of a nickel coin from 10,000 miles away. And so this is just Los Angeles down to South Africa. It gives you about a baseline of about 10,000 miles, which is where you could see a nickel coin from. You know, presumably it would be bright enough, right? And so there's one catch on being able to do this technique of using these telescopes separated by a distance to get very high resolution. And so the light from in this case, we have 2 telescopes here, and the light from the 2 telescopes, when it hits the camera in your beam combination lab, it has to hit the camera at exactly the same time from the 2 telescopes. And so what we need to do is, because the telescopes are spread across the mountaintop, your light is going to hit one telescope before it hits the other. So what we have is this optical delay in a laboratory that we equalize the path lanes. And so this is just a little movie as the star moves across the sky, the telescopes follow it, and you have these delay line carts in the lab tracking the motion on the sky. And so the CHARA Array itself was built and is operated by Georgia State University in Atlanta, Georgia, and they just needed a nice mountaintop to put it on, so they ended up deciding on Mount Wilson Observatory to locate it at. And so the CHARA stands for the Center for High Angular Resolution Astronomy, and the center was founded in 1984 by a professor at Georgia State University called Hal McAllister. He founded the center with the vision of building this long baseline array to get exquisite precision to be able to resolve the surfaces of stars. And early on in the project, he hired Theo ten Brummler, who helped with the design and developing a lot of the components in the array. And so the array itself, the groundbreaking for the array occurred in 1996, with our first fringes occurring in 1999. And routine science operations with all 6 telescopes in operation began in 2004. And so far we have almost 300 publications. So funding for constructing the array came from the National Science Foundation, Georgia State University, W.M. Keck Foundation, and the David Lucille Packard Foundation.
How much?
It's about $14 million altogether. And so, as I said before, there's 2 components of CHARA. There's the Center for High Angular Resolution Astronomy on the campus of Georgia State University in Atlanta, and that's led by our director, Douglas Geis. And then we have about 17 staff members who work at Mount Wilson itself, and that we keep the array running, build new instrumentation, and help astronomers from around the world use the array of telescopes to collect data for the science project. And those of you from Griffith Observatory might notice Evan here, who's also a guide at Griffith Observatory, who's one of our nighttime telescope operators. And in addition to Georgia State University, we have partnerships with several other institutions who have built instrumentation for us, provide expertise, and provide access to the community so that astronomers from across the US and around the world can apply for time at the CHARA Array. So I'll just take you on a quick photo tour of the array. This is one of the 6 CHARA telescopes, and so they basically all look similar to this. On the side of each telescope, there's an adaptive optics board. So there's circled in red at the top here, there's a deformable mirror. And the purpose of this mirror is basically just to counteract the motion of the atmosphere to try to give you as clear of an image as possible to send the light into the laboratory. From the telescope, we send the light through these vacuum pipes. And so we're sending the light across the mountaintop into this central beam combining lab. And here you can see the 3 arms of the interferometer, the vacuum pipes all leading into the lab. And so inside the lab, this is where we compensate for the delay correction. So there's 2 phases. There's these vacuum pipes underneath the rails where we can insert these mirrors that pop up into the path, and you can add a certain segment of delay that gives you access to a certain part of the sky. And then we have these delay line carts that drive along the rails and continuously move across the night to equalize the path length. And basically, these rails are 45 meters in length, and depending on where your target is located, it might take about an hour or 2 for a cart to move from the front of the rails all the way to the back. So very fine motion. And then from the rails, it comes onto these, what we call these beam-reducing telescopes, and it basically takes the light beam from about 12 centimeters in size down to about 2 centimeters. And then after the light gets compressed, we have a second adaptive optics system, one for each telescope, in the laboratory. And this basically corrects for any slow distortions that the light encounters from the telescope into the laboratory. And then after it goes through the adaptive optics system, we have a beam splitter that basically separates out the visible light and the infrared light, and it sends around the corner to one or sometimes more than one of these optical tables. And each one of these optical tables is where the magic happens of that. We combine the light together and record the signal of what your star looks like. And each one of these tables has a different strength. Some of them combine all 6 telescopes of the array and are our main imaging combiners. Some work at near-infrared wavelengths, others work at visible wavelengths, and some only combine 2 or 3 telescopes but have very high sensitivity. So depending on what object you're looking at, you might decide to observe at one or another of these combiners. And this is just a little movie showing one of the telescopes in the CHARA Array. So this is the telescope. The covers on the telescope all operate remotely. So the operator sits in the control room and can control this. This is the adaptive optics bench on the side of the telescope. So it goes through some optical components and down through a little cover here. And from that cover, it gets injected into these the vacuum pipes. And here you can see the top of the beam combining lab and some of the vacuum pipes there. And the laboratory itself is a building within a building. So the inner lab has as stationary air as possible, just to minimize any kind of distortions in the light beams. These are all the computers that control the delay line carts and the different cameras in the array. And then this is going into the lab. These are the 6 tables that reduce the beams. And here are the rails. And pretty soon you'll see the carts. And see, these are the carts moving a lot faster than they do at night. But they just go up and down the rails depending on where the star is located. And then this is our switch yard that separates the visible and infrared light and sends the light to any of the beam combiner instruments over here. And this is, again, where the magic happens, and that we combine the light from all 6 telescopes and record the signal on the camera. And so these array of telescopes operate a little bit differently than regular telescopes. So we're not getting direct images of stars. When you combine the light from these 2 or more than 2 telescopes, what you're actually measuring is an interference pattern. So light is a wave, and so if you combine the light from 2 telescopes together and you match the path lengths exactly, you get these bright and dark bands. It's kind of up in this figure here. And so this is actually what we're recording on the detector. And so if you have a very small star that's unresolved, you're going to have very high contrast between your bright and dark bands. If you have a larger star that's partially resolved, you're basically going to get a fringe pattern at all points across the star. So the fringe pattern from one side of the star is going to blur out the fringe pattern from the other part of the star. So you're going to have very low contrast fringes. So by measuring the contrast of the fringes, that encodes information about the spatial extent of the star. So each pair of telescopes that you have gives you a slice of what the star looks like in that direction. And the more telescopes you have, you can kind of piece together what the star looks like in 2 dimensions. And on top of that, as the Earth rotates, your baselines kind of move on the sky. So you kind of start filling in this puzzle of what the star actually looks like. And so one of the main things that we do with the array is just basic measure the sizes of stars. So depending on what your star is kind of star it is, it's going to have a different size. So the sun is just an average, ordinary star. You can have stars that are much cooler than the sun and also much smaller. You can also have stars that are much hotter than the sun and that are larger. And then, so this is an image, kind of a famous image diagram in astronomy called the Hertzsprung-Russell diagram. And it measures the temperature, and the astronomers, they plot the temperature with the hotter temperatures over to the left side of this plot. And then the other side is the brightness or the luminosity of the star. And so basically the way this plot works is that you have hot, massive stars up to the upper left and cool, low mass stars to the bottom right. And this has about almost 700 stars that have been observed with arrays like CHARA. Basically, the size of the symbols in this, the diagram corresponds to the diameter of the star. So you can see along this sequence here, you get these hot, massive stars are larger than these cool, low-mass stars. And this sequence is called the main sequence, where a star spends most of its lifetime. And then as a star ages, it goes into the red giant branch and gets much bigger in size. So you can actually see this turn off, and the stars get bigger when they're up in this giant branch. And one particular type of star that CHARA often looks at are exoplanet host stars. So these stars are hosting an exoplanet, and there's particular reasons why you want to measure the properties of the host star very accurately. One is that the size and the brightness and temperature of the host star gives you information about the habitable zone around the star. And so, if it's in the habitable zone, there's a chance that that exoplanet could host life. And then another thing is that a lot of time these days, a lot of exoplanets are detected by looking at stars that pass and eclipse the host star. And so you see this dip in brightness as the planet passes across the face of the star, just like the eclipses of the sun we were looking at before. But getting the properties of those planets from that eclipse depth depends precisely on how big the star is. So if you know how big the star is very precisely, you can then refine how big the size of the exoplanet is. And for old stars in the giant bands, some of these are variable stars that change in brightness over time, these Cepheid variable stars. And they change in brightness because they're pulsating. And we can actually measure that change in size as they pulsate on the giant branch. And in addition to measuring sizes of stars, we can actually start getting images of what their surfaces look like. So these are a collection of some rapidly rotating stars. So these stars are rotating so fast that they kind of bulge at the equator and flattened at the poles. And so using the CHARA array, we can measure that size difference between the equator and the pole. And there's a few other effects that you can see. Like as you get closer to the edge of the star, you see that the brightness drops off. This is an effect called limb darkening. And so you can directly measure that limb darkening on the star. And then the one other feature that you notice, that the equator often looks cooler than the poles. And this is basically because the poles are closer to the center of the star, so they'll appear hotter, and the equator is bulged out, so it will appear cooler. And this is an effect called gravity darkening. So you can start studying these detailed astrophysical properties of these stars. And just like the sun has sunspots on it, stars have star spots. And we can start imaging these star spots on the surfaces of the other stars. So these are a collection of 3 magnetically active stars. So they have very, very big star spots on them. They were basically observed over the course of their rotation cycle. So you can see the spots move in and out of the side of the view. And so the images on the top are basically the way the star actually looks in 2 dimensions. And then the bottom images are the surface unraveled, so you can see all longitudes at the same time. So you can kind of see the distribution of star spots on these stars. And then for supergiant stars, you can, they have very big convection cells that they kind of boil up over time. And so these convection cells can also be imaged. So this image on the right is actually a model simulation of what these supergiant stars, Betelgeuse being one of them, might look like. And this is a supergiant star called AZ Cygnus. And you can actually start resolving these convection patterns. And if you take images over time, you can see how these convection patterns change on different time scales. And with the high resolution of the CHARA array, you can also look at binary stars. So this is a multiple star system called Sigma Orionis. So it's actually a star just below the belt in Orion. And if you look at it in a single telescope, you'll notice that it's a multiple system with 5 different components there. Here in this image, you can't break apart the A and B pair, but in reality, that A component is actually 2 very close stars with an orbital period of 140 days. And And so you can measure that period over time. And if with binary stars, if you measure their period over time, and you can measure the size of the orbit, is a way to get the masses of stars, because they're being held together by gravity. And so these are two massive O-type stars with masses of 17 and 13 times the mass of the sun. And you can look at even closer binaries. So this binary is an interacting binary. So it has a companion star, and this one star has evolved into the giant branch. So it has the outer layers of the star has expanded, and if the outer layers get too close to the companion will start pulling material off of the star, and it'll form this accretion disk around the star. And so when you look at it with the CHARA array, you can get the orbital period, so you can see the stars going around, but you can also start seeing that the evolved star is tidally distorted, and that the companion star has some elongation from this accretion disk of material that's flowing around it. And you could also do very high contrast binary. So this is a popular star. It's the Polaris, the North Star. And so this image on the left hand of the screen is just the Polaris there at the end star and the Little Dipper. Polaris has a wide companion. It's Polaris A and Polaris B. And Polaris A itself was known to be a very close binary with a period of about 27 years. And it was resolved for the first time roughly around 2006 with the Hubble Space Telescope. So basically, Hubble got these points on this farthest part of the orbit, but as it started moving closer, the distance between the two stars started getting even closer, and too close for the Hubble Space Telescope to resolve. So we started looking at it with the CHARA array, and these green points up here are all CHARA measurements. And so we start filling in the orbital motion of the close companion of Polaris. And Polaris is one of these Cepheid variable stars, these pulsating stars. And so you can actually measure that the size of Polaris changes just a little bit. It's not a very big pulsation. Changes about 4% in size over its rotation period, pulsation period. But one of the surprising things, when we took the data, there was a lot of structure in the images. And so when we got the data with CHARA, we were like, oh, let's try to reconstruct an image of what Polaris looks like. And when we did that, it turns out that Polaris itself is a spotted star. So there's these spots on the surface, and they change over time. And they might be linked, they could be linked to pulsation. The pulsation period is about 4 days. But there's also it's been measured recently, the brightness of Polaris changes over a period of 120 days. So this might be a rotation cycle. So it could be that these spots rotate around over that period. So the investigators that did this work are continuing the program, just kind of investigate the what might be the cause of these spots. And this is another binary that CHARA observed. This is an eclipsing binary, so it has a companion star, and the companion star actually isn't seen. And the companion star passes in front of the supergiant, the primary supergiant star, every 27 years. And it has this the brightness goes down and stays low for about over a year, and then comes back up in brightness. And so it was hypothesized that this hidden companion that you don't see might be hidden in an opaque disk of material. And so the last time it went through eclipse was back in 2009, and this is a pre-eclipse image. It just looks like a normal star. But as the eclipse progressed, you started seeing this Pac-Man shape of the bottom half of the star being blocked out. And as the eclipse went along, you started seeing more of the eclipse, more of the star, bottom half of the star getting blocked out. And you kind of, if you kind of stitch all these images together, you kind of see this silhouette of this dark disk of material that is passing in front of the star. So presumably there's a star inside here that is orbiting around this big star. And we can also look at disks instead of in silhouette, but also disks directly. So these would be like protoplanetary disks around young stars. These are disks of gas and dust that form around young stars and will eventually be the sites of planet formation. And so this artist conception here has like little planets forming in this disk. And so with the CHARA Array, you can start looking at the inner regions of these disks around young stars. This is the star V1925 Aquila, and the star is in the center. It's just modeled as a bright spot there, but you can see this nice ring of material around it. And it has a bright spot, and these images were taking about a month apart, and you can see that some motion in that spot. So there's some clump of materials going around in this disk. So, so this is a very young star. You can also observe stars near the end of their lives, and so this is one type of star that ends in a nova explosion. So classical nova explosions happen when you have stars in binary systems. So one star itself is a white dwarf star, which is like the end product of basically a solar-like star, ends up as a white dwarf at the end of its life. And if it has a companion star, and that companion star evolves into a giant star, some material could spill down onto the white dwarf. And if enough material builds up onto the white dwarf, eventually it'll explode off that material that built up on it in a nova explosion. And so we were lucky enough to catch a few of these nova explosions that were bright enough that we could observe with the CHARA Array. So this was Nova Delphini in 2013. So it was actually, the nova itself was discovered by an amateur astronomer in Japan who happened to be looking at the sky and noticed, hey, there's a nova that went off. There's suddenly a bright star that you didn't see before. And so about a day after it was discovered, we decided, oh, let's point the telescope of the CHARA Array to it. And we just got a very marginal result. So we're like, hey, let's look at it the next day. And it got a little bigger the next day. And so we basically followed the expansion of the material away from the central star over the course of the month. So we get the expansion of the nova. And on a few days, we actually could observe with all 6 telescopes of the array, and we get these images of what that nova looks like. And so this is kind of like a diagram of what the nova looks like, of a compact core in the center with this more diffuse material that is cooling off and expanding outwards as the material expands away from the central star. And then in 2021, there was another nova in the constellation of Hercules that looked very different from Nova Del. So this one kind of had this bipolar lobe. So this is 2 days after the nova exploded, and this is 3 days. And so the structure is changing a lot. So this is kind of an artist's conception of what might be going on here, so that you have this bipolar material going out and a perpendicular outflow that's not going as fast, like kind of in the equator of that. And then this is similar to the story about Betelgeuse that you heard before. So this was Betelgeuse a few years ago, as you heard before, went through this great dimming that, there's now a gas cloud that was blocking it. So this was another very large hypergiant star, RW Cepheid. And so it went through a similar great dimming period like Betelgeuse did. And that you can see this dark structure in the star. And so the idea here is, you've seen this graphic already tonight, that they likely ejected material, and if that material is coming away just along your line of sight, you'll see this big dim spot where that material was. So this part of the star here was dimmed out. And then CHARA has observed one extragalactic observation. So it's looking at the active galaxy NGC 4151. So this is a nice Hubble image of the galaxy. And in the center of this galaxy is a supermassive black hole. And it's an active galaxy, and which means that there's material actively accreting onto the supermassive black hole in the center. And there's all these jets and everything that happen in the center. And so this image here is another HST image with a radiojet that you can see in there. And so this is just in the central region. And then what CHARA can see is just in the center of that image. And so we can actually measure the elongation of that dusty disk in the center of surrounding that supermassive black hole. And it basically, you can see that disk is perpendicular to the outflow that you can see in the radio wavelengths. And then I thought I would end by saying some of the new developments that we're working on at the array. So we're currently working on a future expansion of the array, of adding a 7th telescope to the array, but this telescope is going to be a mobile telescope. So the telescope itself is a 1-meter plane wave telescope, and the dome for that telescope sits on this trailer that we could potentially move from one site to different sites across the observatory. And so we have two sites mapped out initially. So in this image, the blue circles are the existing telescopes. So our first position for this new telescope is going to be right next to our closest pair of telescopes to give us this little small triangle. And so the goal of this small triangle is to actually observe stars that are currently too big to resolve with our baseline. So these stars that are really big, like Betelgeuse, for example. So we want more short baselines to observe those really big stars. And then once we commission the telescope there, we'll plan to drive it down the observatory road and basically double our resolution, give us almost a 600-meter baseline for imaging stars that are even smaller. And one of the novel aspects of this project, so currently we send the light through vacuum pipes to our beam combining lab. And so with this mobile telescope, we're actually going to use fiber optics. So we're going to inject the light into a fiber optic cable, and that cable runs underground into our laboratory.
How much is the cost?
How much does it cost?
Yeah.
Oh, it is like maybe like $1 million for the telescope, and the fibers themselves are quite expensive though, because the fiber lengths are about 650 meters long. So it's a few $1 million project. And this is we installed the plane wave telescope in 2024. And so this is a crane, and you can see our two close pair telescopes here, the S1 and S2 telescope, and the plane wave being installed there. And the night that it was installed, we just got some nice images of galaxies. So not interferometry, just nice images. And then later in 2024, we dug trenches, laid the fibers down. The fibers themselves are 650 meters, and any telescope that we will combine with this new mobile telescope also has to have a fiber. So we have fibers for each of the existing telescopes. And we're working on, we've sent a laboratory source out and gotten some of these interference fringes, and we're working on getting those fringes now on Sky to commission these really long baselines. And one of the goals of this is that these white lines are the existing arms of the interferometer. This solid red triangle is with that new site that would give us the almost the 600-meter baseline. And we also mapped a site just outside of the observatory grounds that in the future we might want to bring a telescope there, and this would give us a kilometer baseline, and that would actually give us the resolution that you would need to, if you had one of these planets that transits its host star, you got to actually resolve the silhouette of the planet transiting the star, which would be kind of cool. And then I'll just end by saying that you can come visit us at Mount Wilson Observatory. So Mount Wilson itself offers docent-led tours on the weekends in spring, summer, and fall. And you can also take self-guided walking tours. If you take one of the docent-led tours, you actually get to go in the telescope itself, and this is just a shout out. I don't think she's still in here, but this is my daughter Emily and my wife Angie, and so you get to go in the telescope domes if you get these docent-led tours. And we have an exhibit hall for CHARA up there, and this the centerpiece of this CHARA exhibit hall is this Michelson interferometer beam. So back in 1920, when the 100-inch was built, they were doing some of these experiments with interferometry then. They put this beam way on top of the 100-inch telescope, and it had two mirrors to kind of simulate a an array of telescopes. And it brought the light together, down. You had an operator moving the positions of the mirrors up there. It sent the light down, and then observer at the eyepiece seeing those interference fringes. And this was the first way that the diameter of a star other than the sun was measured, and that was of Betelgeuse back in 1920. And this is just I think I can just let this play as we conclude. It's just an aerial tour of Mount Wilson.
Yeah, well, thank you for that. Come up and sit down. Yeah, I think we have a little bit of time for some questions. Do we have any questions in our audience? Yeah, here in the front.
Earlier you mentioned the moon's been smacked 104 times in the seismometers monitors that were laid down in the 70s.
Jared question.
The new crater on the moon. So my question is the moon a hollow engineered object? It rings like a bell when it's smacked.
The moon's not hollow. The moon is a solid object. It has a core. That's well-known physics. Another question back here?
Yeah, so for the CHARA Array, what's the limits as to what you can point it at? Can you point it at anything, or is there like a distance limit?
So it's kind of like a distance limit, but it's more a brightness limit. So if you're familiar with magnitudes, for most of the instruments, it has to be brighter than 8th magnitude. And for distance limits, it has to be either large enough or close enough that we can angularly resolve it. so brighter than 8th magnitude, and they're big enough or close enough that we can measure the size.
And in fact, I think when we mention CHARA to people, the comment I always hear is, well, how can we have a big observatory there with the light pollution? Can you just explain? I think that relates obviously to the objects that you're observing.
Yeah. So because we have a very small field of view, and so we're limited to. So background light doesn't really affect us because our field of view is very small, and we're looking at bright objects anyway. Yep. So if you wanted to do deep sky objects, Mount Wilson is probably not the place to go. But because we're basically getting sizes of very bright stars, it's fine that it's here.
Yeah. Another question here?
Yeah, if you eventually got that additional telescope that's outside of the Mount Wilson, that's a kilometer away, like how does that change things again for like what you can then see?
So I'll repeat the question for the stream so they can hear it. The question is, if they get the telescope that's a kilometer away, what does that change about the instrument?
Yeah, so the kilometer baseline is basically the resolution of the array is being set by the distance between those the telescopes. So that 1 kilometer baseline is basically going to give you a factor of 3 improvement in resolution of what we can currently do. So it would be the highest angular resolution you could do. So very small objects you can resolve. So.
Yeah. Another question here, and then we'll go to the back.
You had mentioned earlier dust coming from stars, which was how scientists or astronomers are able to make a certain determination. Can you say more about this dust? I mean, that sounds, a little bit odd when you just say dust coming off of a star.
Yeah, so this would, I guess, it would be these either supergiants or the hypergiant stars. So these are stars that have very active surfaces. So materials are kind of like boiling up and flowing down. And so occasionally if energy just increases, like even I think on the eclipse photo of the sun, you see so these prominences. So there's material coming off like a star like the sun. And so if you have a star that's much more massive and has a lot more energy output, you might get these big ejections that come out. And as it cools, like dust can form in that material coming out. Yeah. Do you want to say more?
Not really. Well, yeah, it's these supergiant stars like Betelgeuse. The winds that come off can blow the outer atmosphere out. And exactly what Gail said, that as it cools, you can form dust grains. That physics of how that happens, I don't believe is super well understood. But we've measured these dust grains all over the place. Dust is common in the galaxy.
Yeah, what we've shown, in fact, Wolf-Rayet stars, which have these shells kind of coming off, they're windy stars, and they have, I think, similar kind of processes I actually wanted to ask you regarding, you mentioned the novas, and we are all waiting anxiously for nova, I think in Corona Borealis. Is there any news on this, or is it just?
Yeah. So there's actually a program for one of our community access programs that has a long-standing program that if T-Corps goes off, CHARA will observe it.
Okay.
So we've done some preliminary imaging and just measuring the size of it, and it looks like the size has some very marginal evidence that shows that it could be like changing in size.
Okay.
So it needs more observations to, so it could be like, precursor to,
nova.
We'll see.
the nova that goes off.
Question up in the back there. Last question from our audience.
Hello. So recently there was a discovery of a companion of Betelgeuse. Have you had any observations take place at CHARA to try and study this newly discovered companion?
Yeah, so Betelgeuse presents a challenging issue for CHARA because it's so big. So it's almost the size of it in angular scale is 40 milliarc seconds. Wow. But that's essentially like the resolution of like the Hubble Space Telescope. So it's a huge star angularly. And so when we look at it on the CHARA array, the fringe pattern that we see is very, very weak. So even with the smallest baseline, we're sampling way out on this curve. So we're getting like, the equivalent would be if you see the whole surface of Betelgeuse, you're only like focusing in on a clump of material on its surface, right? And everything else is washed out. So it's very hard for us to get data. So we have collected, when it was going through its great dimming, we collected some data, but it was only on like the closest pairs of telescopes that we have. And so it's the data that we collected is hard to go back and see if there's a companion there, but we have one investigator who's currently looking to see if there's evidence for the data that we collected. It just is a challenging target for us just because it's so big.
It's too big. Yeah. Well, let's thank our guest again. Thank you so much for joining us tonight. Fascinating stuff. And folks, next month we have a very special guest at All Space Considered. We'll be joined by Dr. Katie Mack, the Hawking Chair in Cosmology and Science Communication at the Perimeter Institute for Theoretical Physics. Once again, All Space Considered is brought to you by the City of Los Angeles Department of Recreation and Parks. We also like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. I also want to thank everyone that's involved in the creation, in the streaming of All Space Considered, the presenting of All Space Considered. There are a lot of people that make this show happen, and they all deserve recognition. So I appreciate all the effort that makes All Space Considered possible every single month. And thanks to our audience for joining us tonight. We'll see you next month. Thank you, everybody.